Hello, everyone. Today I would like to share some of the things I came up with during the course of my PhD thesis. And since we're short on time, I'll just get onto it. So this talk is on Tripos models of internal set theory, which is an attempt to categorify a certain kind of set theory developed by Edward Nelson that had the purpose of creating a syntax that makes the methods of non-standard analysis more accessible to mathematicians that are not as well acquainted with mathematical logic. So the set theory consists of just the usual ZFC set theory, together with a new unary predicate, so you can think of this as a coloring on the universe of sets, telling you that certain sets are deemed standard, and some axiom schemes to govern this new standardness notion. And this is where we get the new proof methods from. So the first one is the following. If I have a formula, which is just a formula from usual ZFC, so it doesn't involve the new predicate, we call those internal formulae. So if I prove that something is true of all, so a internal formula holds for all standard sets, then in fact it holds for every set. That's transfer. We have standardization. So we no longer have separation for formulae that are internal, but we get the next best thing. So if I take any formula, then there is a unique standard subset of a given standard set whose standard elements are the ones satisfying the formula. We don't know what happens to non-standard elements, but we know the behavior of the standard elements. And we also have idealization. If I have an internal relation, then saying that there is a set that relates to every standard set is the same as saying that I can find a set that relates to all the elements in the standard finite list. Okay, so the idea here is to first note that if I take a model of internal set theory, then the subcategory of the standard sets and maps is in fact a topos, and the inclusion functor creates finite limits and subobject classifiers. And the idea behind this is that all the usual finite limits are given by some internal formulae, and the contrapositive of transfer tells you that if there is a set satisfying those formulae, then there is a standard set satisfying those formulae. So that is the cruxes of it. And we will analyze this theory by making use of the idea of triposes. So a tripos is just an attempt to extract the logical content of a topos, which you might want to think of perhaps as the logical analog of a Grothendieck site for Grothendieck toposes. So a tripos is a first-order hyperdoctrine with a generic predicate, and by that I mean we have a pseudo-functor from C-op to Heyting pre-algebras, so the pre-ordered analog of Heyting algebras. And this takes an object to what we want to think as the algebra of predicates over that object. And for each map, we have the substitution functor PF that preserves the Heyting structure and has both a left and a right adjoint that plays the role of quantifiers satisfying the Beck-Chevalier condition. And saying it has a generic predicate just means we have something that essentially plays the role of the subobject classifier of a topos. So if I take any predicate, then in fact there is a classifying map in the base category C, such that that predicate is isomorphic to the substitution of that classifying map applied to the generic subobject, the generic predicate. So the interesting fact is that every tripos induces a topos, and conversely, every topos has a canonical tripos, which is just the tripos with the predicates given by subobjects of its objects. Very well, so the point of view is that we have a few hyperdoctrines whenever we get a model of internal set theory. And they come up in a syntactic presentation and a semantic presentation. So we have a tripos over the topos of standard sets consisting of the internal first order delta naught formulae with standard parameters, and semantically that is just a tripos of standard subsets of standard sets. Then we have one that corresponds to the tripos of all subsets of sets, and those are just the internal formulae by separation. And then we have, and those two are triposes, and then we have a hyperdoctrine of all the formulae of IST that we actually might want to see if it is the doctrine of subobjects of some extension of sets. So for example, the topos given by the ultrapowers of sets would work here. So the idea is that IST can be thought as just ZFC with different quantifiers instead of with a new predicate. And then the axioms of IST are just there to tell you how these quantifiers work. And Tripos theory is the perfect tool to deal with a change of quantifiers. So the axiom schemes, the core idea of IST corresponds to relationship between the triposes, rather hyperdoctrines. So the first observation is that if I get a first order hyperdoctrine P, then the index transformations that are idempotent meet semilattice homomorphisms are actually quite interesting. So their fixed points admit the structure of a high-degree algebra and can be made into a first order hyperdoctrine over the category C. And the reason why we care about this, which is actually not generally a subtripos even when P is a tripos, is because there is what I call the standardization transformation on the hyperdoctrine X that takes a subset of a standard set to its standardization, the thing we get from the standardization axiom of IST. And the resulting doctrine of fixed points is actually equivalent to the tripos of standard subobjects. And then we might look at this kind in more generality in abstract at this kind of fixed point doctrines for a hyperdoctrine P. And we add one more property that actually makes it behave like a tripos of standard sets. And this is just to ask that the operator satisfy a reciprocity formula, so a kind of Frobenius reciprocity, but for implication. So I'll call such a transformation a standardization operator on P. So with that, I might formulate the following standardization axiom for arbitrary hyperdoctrines, which is to say there is a standardization transformation on P. What about transfer? So the relevant result here is that if I happen to have a model of IST, actually a structure that satisfies all of the axioms except for transfer, and whose standard sets and base maps, those are just standard maps that map standard elements to standard elements, form a topos with an inclusion that creates finite limits and preserves subobject classifiers, then transfer holds in that model precisely if there is a dominant open geometric morphism of hyperdoctrines between one of the triposes and X. So the one of corresponding to the fixed points of the standardization operator. So we might say that transfer corresponds to the existence of a conservative height transformation of hyperdoctrines. And I'm not saying dominant due to some particularities of the set theory making it be dominant rather than just conservative. We don't actually need dominance in general. So the reason why this is good is because there is a translation that can be done, and we can actually reason using internal set theory inside a tripos that has this kind of structure. So the first result is if we have Q in the fixed point algebra of a standardization transformation, so we might want to think of that as a standard formula with standard parameters, then transfer actually holds in the logic of P. And for our standard here is short for certain thing that you can build out of the transfer morphism. And similarly, if I have just a predicate in such a tripos model, then standardization also holds in the internal language of the tripos. So since we also have a soundness result for triposes with respect to intuitionistic set theory, The idea here is that if you have a proof in the Tripos P that makes use only of intuitionistic IST, then in fact it will hold in the Tripos P. I have omitted talking about idealization due to the length of the talk, but you in fact also have a characterization of idealization in terms of properties of the doctrine P. So that's what I had for this time. Thank you very much for listening. And here are some references.